All right, good evening. Today is going to be class 11 of FoP. We're going to finish off big O notation and common problem solving formulas or algorithms. I don't know why I said formulas. And then afterwards, we're going to begin searching, recursion. And as we go, we're just going to use different methods of solving problems. Back to what we were discussing about the Grok's algorithm. The book was posted in the Slack channel for both the pre-work and the FOP. Definitely do give it a try, especially if some of the subjects that we discussed this evening and tomorrow go over your head. And that's okay if it does. Uh, at least for like personally for myself, I struggled with it, so it's okay. Some stuff seems to be a little bit more difficult than others for some people, specifically stuff like recursion. Um, and it's okay if you don't understand it right away. This is more of an introduction just to get you guys thinking about uh, data structures and algorithms and understanding that computer science and software development are two different things, right? Computer science, it's its own demon. Uh, you might you're gonna learn full stack development in the immersive program and how to how to code, how to make an application. But you're gonna realize that computer science in itself um, is its own headache. Um, so we'll introduce you guys to that today. You'll get a little bit about it in the immersive program. Um, but if you want to get a better understanding of it, I would definitely check out that book I posted. Very helpful, nice pictures to really understand, especially if you're a visual learner. Um, and it really dumbs it down. It's something I needed, and I'm sure it could be very helpful for some of y'all. Um, but yeah, so we'll move forward. Go ahead and share my screen. We're going to do big O and common problem solving patterns. We left off with the frequency counter dot pi. Um, I know we talked a little bit about it prior to it. It's a very common leak code problem that you might encounter where you're essentially counting how many times something appears in your code. And I'm gonna allow you guys to try this out before we walk through it together. Uh, See if you guys are able to uh, try it out yourself. The solution is right afterwards in the slides, I believe. Don't look into it too much. If you want to try it out, you'll see a not so great solution and a better solution. Uh, Try both of them out. Since it's already here, I'm not going to code along. I'll discuss about what's happening in the code, but I'll allow you guys to try it out real quick. We'll give it, a good 10 minutes, let you guys actually attempt to do it before we actually talk about it. So take the next 10 and hopefully it goes good for y'all. All right. So that concludes the 10 minutes. Uh, so let's look at the problem that was given to us on the frequency dot pi. Give me a second. My kid just walked in. Be right back. Sorry about that. Yeah, so let's look at uh the code. So the frequency constant dot pi, it wanted us to write a function uh called same, which will accept two lists, right? And the function should return true if every value in the first list has its corresponding value squared in the second list. The frequency of values must be the same. And then we see an example here where let's see if we can make this a little bit more readable. Um, where it should be able to take in the two lists and it'll return true, false. And then we can see here the first one returns true because 1 squared is 1. We see here one time, both on both sides. 2 squared is 4. You only do it twice here, right? So it only appears frequency once here and then once here. And then same thing with the 3 and the 9. 3 squared is 9, and they only happen twice here. And you see that on line 2, 1 squared is 1. That's good. 2 squared is 4, but it's not here, right? So it doesn't happen to be on the second list, so that one returns false. And then the third one, 1 squared is in here, 2 squared is in here, but the frequency is twice, and that's wrong. So it returns false, right? So incorrect frequency. And going back to the solutions, if you guys were able to finish it, we'll talk about both solutions that we see here. You're given a not so great solution and a better solution. And who can tell me the difference between both of these? Besides it being multiple more lines of code, why is one better than the other? If you guys have the slides, please look at the slides. If not, we'll talk through it, right? So the not so great solution, it takes the two lists, and the first thing it does, it's going to compare the length of both lists to ensure that, first and foremost, like, does it have the same quantity of items in the list, right? So if right off the bat one list is shorter than the other, then we know the frequency is not going to be the same. So that's an easy way to eliminate those, because that's going to be an edge case, right? We might have less amount of integers on one than the other. So we check that edge case right off the bat, and if not, right, if it does not come back false, then we know it's all the same length. Then we can start checking through it. So on line 4, it begins a for loop, and we do for I in range and whatever the length of list 1 is going to be. So length of 1 could be like 4 items or 5, whatever. It's going to loop through that many times, and as it goes through, it declares a variable called square num, and in this variable he is squaring every single item in that list, and he's grabbing it using the index, which is going to be determined by whatever I is within the for loop. And then here's where it becomes a not so great solution. On line 6, it goes, if square num is not in list 2, well, we know that both of these are lists, and when you use a not in or in, it's going to check the list in a searching method, right? And searching in a list is, well, what type of big O notation would we say that this is? What would be the time complexity for searching in a list?
O of n.
O of n, yeah, that's right. And it was already O of n the first time it started a for loop, n being the length of whatever list 1 might have been. And now within this list, we started another loop, right? Looping through whatever length list 2 might be. So now this just became O of n squared. So it became a not so great solution, due to the fact that now this is a nested loop, right? Worst case scenario could be, what if list 1 is the length of a million different integers, and list 2 is like 2 million integers. Worst case scenario is you would multiply 1 million by 2 million, and that would be your worst case scenario of how many iterations you might have to go through, and that's not so good, right? So that's how this one checks it. It searches through list 2, and if it's not in there, it returns false. It'll give you the correct solution if by looking at this code, it looks like eventually you'll run into the correct answer, but it's not effective, right? It's O of n squared, and that's not the type of time complexity you want. And now looking at the better solution, this one is O of 1. And let's talk through it. So it starts off the same as the other one does. It checks if list 1 or list 2 are the same in length. If not, it returns false. But where it does different here is it declares 2 empty dictionaries on line 4 and 5, right? One for the first list and one for the second list. And these empty dictionaries are going to be used to be able to keep track of the frequency of our numbers. So we do start a for loop here on line 6. So right off the bat, becomes if O1. So the time complexity right off the bat, the bare minimum is going to be O1. The fact that we already started a for loop. So throughout the for loop, we're checking if num is in list one freq dictionary, right? But unlike the previous solution, where it's checking a list, when we check a list in this manner, it uses a searching. This one's different, right? This one is going to call the dictionary, and we know when we access stuff in the dictionary via a key, it's going to use an O of one time complexity, right? Dictionaries are going to be an O of one. It's going to be instant. It doesn't have to search through anything specific. It's going to plug and play that num in some form of bracket notation, and it's going to call that key. And if it gets something in return, then it exists. If not, then it's going to be is not going to be there. So checking in it is going to be O1. So this is not a nested for loop. So although line 7 is O1, we said the bare minimum of the time complexity this solution is going to be O(n) because it's already using a for loop. N being worst case scenario, the length of what list 1 is. So it checks if num is going to be in the list 1 frequency dictionary. If so, then it's going to increase the count of whatever value it has assigned. And we see that here by the way it calls it. It calls into the dictionary, uses the num key, and then plus equals, therefore increasing the count that is assigned as its value. And if for whatever reason it's not currently present, then we're going to assign it a starting value of 1, right? And that's how it goes through list 1, and it does the exact same thing for list 2. So essentially, it loops through the initial list and is just sorting it and keeping a track of how many times it's appeared using the key value pairs of the dictionary, right? Giving you still, an O of n time complexity because you no longer have those nested for loops. And once it gets through line 7 and 15, we get into the main meat and potatoes of what the solution is checking for. It does for key and list 1 frequency. It essentially loops through the dictionary and is going to grab the key. It's going to square it, and it's going to check if it's not in the other dictionary, right? And once again, this is still a O of 1, right? Because whatever result you get from squaring the key from list 1, it's going to use that as a way to access the dictionary in the list 2, using that as a key. And it's going to return false if it's not in there, right? And then if it is, we're going to check if the value in list 1 frequency is equal to the frequency that we have in the list 2 frequency, right? To ensure that it only appears so many times. And essentially, it does everything that we did on the previous one, but a much more effective manner where it's not doing nested for loops. Therefore, the overall time complexity of this would be O of n, right? Alrighty. Everyone still with me? I saw Roger Lee, you're staring at your computer for most of the 10 minutes. Were you confused at any point? Do you need for me to clarify anything?
No. Just need to just go back over the slides and just
Yeah,
this
okay.
video again.
Yeah, it's understandable. Um, yeah, so that pretty much takes care of the frequency.py one. Next one is going to be your anagrams.py. We don't have much of an example of code for this one, so this one I'll code along for you guys afterwards. But do give this one a try. Anagrams.py.
Just checking to
Yeah,
make
let's
sure that the frequency is the same. If you don't
yeah, so
have the
the last
last
two if
one,
statements,
it'll
right?
say true.
Because remember, how did we? essentially assign the key value pairs. We assign the actual number itself, and the
Mm-hmm.
key and the value was the counter, right, of how many times it's appeared in that list. So that's what it's checking. It's checking if, for example, let's say we have we'll use this bad boy real quick um, to ensure everyone understands, because I do understand it can get a little confusing. Uh, so we had a dictionary. Oh, I'm sorry, we had a list. Where we say list one is equal to 1, 2, and 3, right? And then list two, we had, let's say we have 2, 4, and 9, right? And then they had the dictionaries list one freak is equal to open and close brackets. List two freak is equal to open and close brackets. Now, what happened was we went through a for loop, right? We looped through the first one, and the code checked is number one from list one currently in my list one frequency. If it's not, then I want to assign it in here and give it a value of 1, right? And then it continued through the for loop. Now, it went to 2 and check how many times it was in there. And it did that throughout the entire code, right? So it checked every single item in that list, and then if it was in there, it would increase its value. If not, it would set a base value of 1, right? Because the first time it encountered it. But let's say we had 1, 2, 3, and then the fourth number was 1 again. Then in the check, it said if it isn't there, we would increase the value by 1. It did a plus equals of 1, therefore this became 2. It didn't reassign another key value pair, right? Because it's already encountered in here. We're tracking the frequency on the value side, so it's increased its counter, right? Let's say list 2 also had a fourth number, and that one was 2, right? So this ended up being 1, 2, and then this is gonna be 4, 1. This should be 9, 1. Why? Well, because 1 squared, right? 1 times 1 is gonna be 1. So it appeared. Well, I did this wrong. My bad. It should be 1, correct? Am I dumb? Essentially, it should be 1, 4, and 9, because 1 times 1 is 1, 2 times 2 is 4, and 3 times 3 is 9. 1 times 1 is 1. So the 1 squared should be in here and should come out twice. So same concept, right? On list 2 frequency, this number appeared twice. So therefore, the value should match the value in list 1 as well. Does that make sense? So that's what I checked. The first if statement is going to check if 1 squared is it in the list 2 frequency as well. If it's not, then that means it's not correct, right? We have to have the squared version of that number in the other list as well. That's what the first if statement does. The second if statement is going to check its value, right? How many times did it appear, right? And we already saw that on this one, it appeared twice, so it should appear twice again on list 2. So that's why when it checks the if-else statement for list 1 and list 2 frequency, it's going to check its values and compare the values. That's what that is doing. Does that make sense, Adrian?
Yeah, kind of. I'm probably gonna have to just do a little bit more research to understand it.
This isn't really something that you can really do research. It's either, honestly, I hate to say it, it's either you understand it or you don't. Let's change the numbers, right?
I
Let's change
think
the
the
numbers. Let's change
syntax is just confusing me, not necessarily the concept.
the syntax.
Yeah.
Okay. What about the syntax is confusing exactly?
So when you were explaining the first if statement, I understood that it's checking the keys in the first dictionary for the first list, right? And it's just multiplying or squaring it and seeing if that's equal to the key in the second dictionary, which would be the result of it squaring it. So if it wasn't that, it'd return false. And then I'm not too sure what happens in this next one. Are we accessing the values now within the dictionaries?
Yes, you're accessing the value. Where it says if list underscore one underscore freak and then bracket key, that returns the value, right? So if the key is 1, it should return a value of 2, right? And then same concept. So let's actually change this. This is gonna be 2, and then we'll say this one's 4. Because I changed the numbers here, right? So this should 4 times 4 is 16. Or am I wrong? No, I'm correct.
You're right.
I'm kind of dumb, man. So we did this. So that means 2 appeared twice, right? So the key 2 with a frequency of 2, and then 4, a key 4 with a frequency of 1, then a key 3 with a frequency of 1. So that's what that one should be. This one is going to be the squared value. So 4, it appeared twice. 16 appeared once, and then 9 appeared once, right? So let's say we're checking the 2. So it does if list 1 frequency key 2, right? It checks 2, so it returns its value, right? We're accessing it using the key, therefore this returns the value. They should be 2 because it appeared twice, and it's going to check list 2 frequency, whatever 2 squared is. What's 2 squared? It's 4. How many times did it appear? It appeared twice. It's grabbing the same item, but on one list, it's squared. Does that make sense? Right? Because on one list, it's supposed to be its base number. So list 1 has 2. What list 2 should have is 4 because that's its squared value. That's why it squared it in the key. Because technically, on the other list or the other dictionary, it's a squared version of it. Right? But it's
Right.
both returning the value for both of these.
Okay.
And the value is holding a number which relates to its frequency that it appeared in our list. Is everyone else with me? Does that make sense, Adrian? Am I not explaining this well? Should I find a different way of explaining this?
I'll just look it up, to be honest. I don't want to waste the time for the class.
Okay. I'm sorry if I didn't explain. Okay, we can retouch this up again later. Let's actually start the anagram.py. And I'll give you guys 10 minutes for that too. Time is 6:06. Let's come back at 6:16. All right. Anyone want to volunteer their code for the anagram? It's a very common
I'll go
leak code
for it.
problem. I think you guys probably had it in your assessment actually.
It's like, yeah. I'll do it.
Okay. Yeah, let's see it, Donnie.
So I pretty much started off similar to like the last one with the whole tip about the dictionaries. So I went through each string and set up the dictionary with the key being the letter and then the value being the frequency. And then line 17, I checked each key in string 1 and made sure that it was in string 2 to rule out the case of the letters not adding up. So the test case for a rat, a car, obviously. And then line 21 was just checking the values of both uh, string 1 and string 2 dictionary and making sure the frequency matched. And if they match, then that means that they can form a anagram.
Yeah, it's awesome. That's pretty much the exact same. Yep. It works on both. Adrian, were you able to understand it a little bit better, or would you require another explanation?
I think we can talk about it after class if you want. But I was just going through the two lists or the list we were provided in the other example. And I was trying to make sense of it, and I still can't.
Okay. All right. Yeah, we'll definitely deal with it after class. Uh, for the rest of y'all, yeah. So this is pretty much the exact thing. Just using the dictionaries to your advantage and being able to keep counting stuff. You're pretty much just mapping what you have there, being able to access it more accessibly than a list. You can go ahead and stop sharing, Donnie. Awesome. Thank you for that. Let's get back to it. So that took care of anagrams.py. Next is going to be multiple pointers pattern. So this pattern is going to consist of creating pointers that correspond to an index and move towards the beginning and or middle of the string/list based on a certain condition. It's very efficient for solving problems with minimal space complexity. Essentially, this is very useful, especially if you work with sorted lists. Let's see. What's after this? Multiple pointers dot py. I'll let you guys try it before we actually talk through it. You have the solutions right afterwards. Try to refrain from looking at them. But essentially, a quick brief through essentially is you would assign variables to the start and end of your lists, right? And you will increase or decrease the position you're in depending on a certain condition. Um, right? It's like looping through a list, but you're using the start and end a meeting in the middle, therefore uh making it faster to be able to find certain things. It's hard to explain it unless you see it. We'll try it for 10 minutes and then I'll actually talk you through this one afterwards and what this code is telling you of how it's done. Uh, Try to use it as reference, but I would avoid touching it as much as possible to see if you can come up with your own solution to try to understand it. This is pretty much the best way of saying it. Unless you try it yourself, you won't really understand it. Um, you're just going to assign, start is equal to index 0, while start is equal to like negative, like index -1, right? And then you would loop through depending if it's what you're looking for. If it's not on the left or the right, then you would just increase the counter, right? Until you find it. Therefore, checking everything. Are there any questions to this? Give it a try before we actually walk through exactly what it is. All right, I am back. All right, so let's get to it. Let me share my screen. All right, so multiple pointers. So it mainly works for sorted lists is where you'll get your most bang for your buck. And you probably saw that from the multipointers.py example that you guys were given. So essentially what we have to do here is we're given the problem to solve where we will essentially create a function that's going to accept a sorted list of integers, and we should be able to find the first pair where the sum is 0, and return a list that includes both values that sum to 0 or -1 if a pair does not exist, right? And we see the examples here of the output that we should be receiving from these examples, the test cases. So without looking at my code, let's go back to this one, right? So looking at solutions that we have here, a not so great solution. And why would you think this is not so great? Just by looking at this.
Because it's nested.
Yeah, it's nested, right? So it easily can increase the iterations depending on the length of this list. So we did it for I in range, and whatever the length of the list is, it could be 5 items, it could be a million, right? And then for that, we went through that again. We did for x in range of 1 plus I plus 1. So it got the I from the previous for loop and increased it by 1 to give it a different start point, and then the length of the list itself, right? So after that, it checked both of them, right? So it grabs the list with the index of whatever the first for loop starts at, and then it checks the list again, but with a second index that was passed in on the second loop here, which is essentially what I is, but just +1. Therefore, grabbing it starts off at index 0 and index 1. It compares those two, and if it equals 0, then we would return those two numbers in a list format. And if it doesn't ever reach this return statement, it would just automatically return -1. Once it checks the sum of index 0 from the first loop and index 1 from the second loop, the nested for loop will go to the next index, and it'll do that until it gets to the entire list. Once it goes to the entire list at least once, then the top level for loop here will go into the next one, which will be 2. And that's not very efficient, because depending on the length of our int underscore list, this can take forever, right? So we gotta find a much better solution of doing this, and we see that here on the next slide. So right off the bat, we declare 2 variables. One being our left, which we know our lists start at 0, so therefore our left is going to be equal 0, and our right is going to be the length of our list -1. And we say -1 because, once again, our indexes start at 0. So if this was 5 integers in a list, the last index is 4, not 5, because it'll be 0, 1, 2, 3, 4. So if we actually did the length function, it would actually return 5, because technically there's 5 items in that list, but we want the last index, so therefore -1 to compensate for that offset. That will give us both the left and the right pointer, right, which is our pointers that we want to get. And then we would check, while left is less than the right pointer, we will essentially assign a variable called total. We would add both of these, and then we would check if it equals 0 or not. If it does equal 0, then that's pretty much our answer, and we can return it right off the bat. If it's not, and our total is greater than 0, then that means that our numbers are too high, right? So we have to bring those numbers down. We already know that our left pointer started at index 0, and it's a sorted list, so it makes no sense to move from left to right. So we'll move from right to left. Therefore, we lower the increment, the increments by 1. Else, if it's less than that, then we would essentially move from left to right, right? And then if it never reaches the return statement on line 7, then we would just immediately return -1. And this is a much better solution due to the fact that there's only one loop here that that we're using here, and that's the while loop, right? And the while loop will only go to the length of whatever our list is, and that's it, right? Unlike our previous solution, it's a nested for loop. So for for every single item in our list, we would do that same item this many times or that many iterations. This being O of n squared, and this one being O of n, therefore being a much better solution. I'm pretty sure you guys can probably visualize this a little bit better by reading the code. So much more effective than the previous one. But that pretty much sums up our 2 pointers, right? The multiple pointers. Essentially, you have a start and an end point, and depending on what your condition is, what the problem is asking for, or what you're trying to accomplish, then you would plus or minus the index looking for that specific item, right? Um, yeah, and that's our multiple pointers pattern. This is you can use it in other problems as well, so it's something nice and helpful to use um, and have in your tool belt. Next one is going to be student practice unique values.py. This should be another pointer one. We tend to have like 2 problems before we move between algorithms. So try the unique values again, or be on your own first before we talk about it. This one doesn't have any practice code. So I'll walk through you guys with my solution, or one of you guys might volunteer for this one as well, and we'll figure it out. All right. Let's go ahead and continue. Share screen. Okay, so unique values.py. Essentially, we were giving a sorted list, and we had to count how many values within this list were unique and not repetitive. So let's get to it. I got 2 ways of doing it. We'll cover the top one. Actually, we'll do this one first. So I had it commented out, but you were able to use a dictionary, kind of like the frequency one before, where you can declare an empty dictionary, loop through your sorted list, and keep count of how many times something appears, assigning it as a key and increasing the value of it. This part doesn't really matter what the value is. Essentially, is pretty much just ensuring that you don't reassign it as you loop through the list, and afterwards I just return the length of what unique underscore values dot keys will return to me, right? So I don't know if you guys remember when I mentioned about the dot keys or dot values or dot items of dictionaries. What you essentially get back is it's a list, right? So once you actually sort through the entire array and you've assigned key value pairs of stuff that's appeared in your list, and you increase the increments and whatnot. There's only so many items in there that were put in, right? And if it appeared more than once, the value increased. If not, then we assign it. We actually added it in there. So honestly, we just have to count how many keys we have in there, and that's what I did. I returned the length of what the unique underscore values dot keys would give me, which would be a list of numbers, right? But here I actually did the code for using the pointers, and the first thing I checked was if not sorted list, then I will return 0. Pretty much just it would check if it's empty or not. That means there's no unique values. If not, then I declare unique count is equal to 1. Because if there's at least one item within our list, then there's at least one unique count, right? One unique variable in here or integer, right? So that count will automatically start at 1. And then we would do a for loop where we would do the range and start at index 1, right? So we would start at 1. Reason for it is because we already tracking that we have one value in there. So we're going to try to compare the second value to the first value. And that's done here where we grab the list by the index. And it would start by essentially index 1, and it would check if the value before it, which is I minus 1, is the same or not. And we can do that because it's sorted. There's not going to be no weird numbers here. We should know that what comes before it, it's going to be less than or greater than. And then we can just increase our count as we go through if they're not the same, therefore making them unique, right? And you see that here, we essentially we start here at index 1, it checks the one before it, it's the same, so we don't increase the count, and it keeps going through until it reaches the last item. 2, it checks the number before it, it's different, so we increase the count, therefore being 2 unique numbers, okay? Running this, you'll get the answer back. 2740. I'm assuming everyone got something very similar to this. Did anyone attempt it this way as well?
I
Yeah,
did it totally different than both ways.
really. Let's go ahead and see that. That's awesome. If you don't mind sharing.
Yeah. I just need to. So I just used the set function because we did it the other day, and it just pulled out the unique values and just took the length of the set.
Why are you like this, Carol? Yes, that works. Awesome. Yes, that's good stuff, man. That's not that's not the algorithm pattern, but all right. I mean, if it works, it works. That's awesome. Cool.
I was just trying to follow the assignment.
That's cool. Very, very, different minds, but this is a prime example. Honestly, it's all personal preference, right? Both ways can work, right? You saw 3 different ways. You saw one that has a built-in method. Kara took full advantage of that, and it did what you needed to do. I was able to use a dictionary to keep count of frequencies and just return a list, and then we're also able to use pointers. So that's just a prime example of how, at the end of the day, there's different ways to accomplish the goal. Honestly, all 3 of them are just as effective. So, whatever you decide to choose, it's up to you. Personal preference, but you have all these tools now in your tool belt. That's just another way of doing things now. So whenever you do run into a problem like this, you know that there's different ways to attack it. And no way is wrong or right. Whatever works for you, whatever clicks when you're looking at the problem, that's the right way of doing it for you. All right. So just think of it that way. Awesome example. Thank you, Kara. Let's go ahead move forward. So that took care of the unique values. Next is going to be the sliding window pattern. So this pattern involves creating a window, essentially just an area that you're looking between, which can either be a list or a number from one position to another. Depending on a certain condition, the window either increases or closes, right? Very useful for keeping track of a subset of data in a list of string. Essentially, you just be keeping count between one list to another, and depending what the values before, after, whatever you're looking for, you might want to slide this over, so you'll choose something else to assign it here. Get rid of one number, add the next one, therefore sliding it over left or right. And you see here an example of how it looks like, right? So slide one element forward and just pretty much comparing whatever you're looking for within that window, right? And I'll let you guys attempt that real quick before we actually cover it. Just like everything else, we have a not so great solution and a better solution. Use this for reference if you need something to compare it to. But if not, go ahead and do it. Try to refrain from using these as much as possible, and then we'll come back and attempt it together. How'd it go? Confusing? Anyone's thoughts and opinions? Okay. We're going to talk about it. I'm gonna talk about my code. I didn't even look at the not so great solution or better solution, so I'll show mine, and then we'll talk through the great or not so great. Um, mm, 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 mm. Let's see. Can y'all see my VS Code? Awesome. All right. So we had to write a function called max sublist sum, which accepts a list of positive integers and a number called num. So two different parameters. The function should calculate the maximum sum of n, a number of consecutive elements in the list, right? So the sum of these many items in a list, right? So our window is going to be the size of what num is going to be is being passed in, right? So that's what our sliding window will consist of these many integers, right? And let's talk through it, right? So we're giving a list, right? 1, 2, 5, 2. Okay, so it's not in order, it's a bunch of random numbers. We just want to find the sum of a certain amount of integers consecutively back to back. So the example here, the first one is going to be 2. So we want to find out what's the maximum we can find of two numbers that are back to back. So whether 1 plus 2, 2 plus 5, 5 plus 2, so on and so forth. So we have to create a window that we can slide left and right and compare the sums to. So first and foremost, you check your edge cases. I checked on line 9 is the length of the list of positive integers that we have is less than num, then it will return none, right? Because it makes no sense to get the sum of a group of numbers if we can't even meet the quantity, right? And then we declare what our max sum is, and it's done by grabbing our window, and you can see here the brackets are start and end point of what items we want to get from this list. We put nothing on the left side of the colon, therefore the start is going to be the start of our list, right? We didn't declare a specific index, therefore its default is index 0, and then it's going to be up to what num is. So it's going to be 2, right? So 0 and 1, so it's up to, but not including what this is. And num is 2, so therefore index 2 is 5, so it doesn't include that index, it grabs the first 2, right? And that's how we slice through the list automatically. I use a sum method to just get the sum of both integers that is our list. Therefore, this is going to be our max sum right now. Just assign it to the current sum of what we can manipulate through. And now we have our window, right? Our first window are those first two integers or whatever quantity of numbers is being passed into the num parameter. And now that we have our window, we can start actually checking it against all the other numbers we have in here. So we do a for I in range, and our start of the range is going to be num, right? So why? Because we already took into account the first two numbers. We want to start at 2, at index 2, right? So therefore, num is going to be the start, and then the length, the overall length is going to be the overall size of whatever our list is. That's from what the range we're trying to check between. So that's how we're going to initiate our for loop. Our start endpoint is going to be from num to the end of this list. And then we're going to move the window here on line 14, right? we're going to change what the current sum is. And how do we do that? All right. Well, if we want to move, let's say our window is currently right here at 1 and 2. We want to move this to the right and grab 2 and 5. Then technically what we're doing is we're dropping the 1 and picking the 5 up, right? That's essentially what sliding the window does. So therefore, our current window, which is at current sum, is going to subtract what the first item is from its sum, right? We do that here, current sum minus the list of positive integers, and we grab the I minus num, therefore grabbing the index prior to it. And then afterwards, we pick up the 5 by doing plus list of positive integers, and then we actually get that range because we started at num. Therefore, it's just I, right? So we drop the 1 and pick the 5 up. Therefore, moving our list over to or our window to the right. And now we grab a new max sum, right? We compare it. We have the max comparator. This is one of the methods that is allowed in Python, just like min, right? We have max, and it takes 2 different parameters, or you can actually give it more. If I'm correct, you can actually pass the list. It'll get you the max number in that list. Here, I'm just passing it 2 different arguments. One's going to be what the max sum is, right? That's what our current max is, right? Current sum is going to be what the max sum was, and we gave it the current sum a new value. So therefore, we're comparing what used to be max sum and what the new current sum is, and then reassigning that to max sum, right? Does this logic make sense? We're just grabbing comparing the previous sum to the new sum, seeing which one is bigger, and then at the end of it, we are returning whatever max sum ended up being, right? It's being updated as we slide our window. We're grabbing the new sum. As we slide through the entire list, we checked all the numbers, all the different combinations, and we could just return whatever max sum ended up being after we checked everything, right? Does this make sense? At any point did I lose any of y'all? Okay, awesome. So let's check the not so great solution and the better solution. I didn't even read it, if I'm being honest with you. So let's look at it. We check if num is greater than length list, return none. All right, so therefore, same thing. We check the edge case. The data totals is equal to 0. Line 5, we begin a for I range, and then the range is whatever the size of our list is minus the num that's being passed in there. So if our list is 5, and we want to grab 2 numbers, we subtract the number by 1, so 3. Okay, yeah, so it's essentially just grabbing the remainder of whatever is not being added, or is not being needed from the num. It sets a temporary value at 0, and then it starts the for loop from 0 to num. Checking the first 2 numbers in our window. It adds both the I and J. Oh, this is horrible. It grabs whatever in underscore list. It grabs whatever is at index I plus whatever is at index J. And then it compares it to our current total. It pretty much did what we did, but it did it in a nested for loop. Not so great solution. A better solution here, they assign a max sum and a temporary sum variable here. Both started at 0. And then they check the edge case again at line 4 and 5. And we did a for loop for I in range of whatever num is. So they're going to loop the amount of time. So if num was equal to 2 in our example, then they did that twice. And then they added the first 2 items to our max sum. My dog just vomited. I heard him. I don't know if you guys can hear him in the background. Jesus Christ, man, my dog is driving me crazy. Anyways, back to the code. So yeah, so they assign whatever the sum was by grabbing the first item. So this declares their window for them, right? I'm gonna pause here real quick. Just give me a second. I'm so sorry. He's just gagging. He's all right. All right, cool. So yeah, they grab their first sum from their window by looping through the first two items within their range of whatever number's been passing there. They assign that max sum to the temporary sum. And on line 9 through 11, they do for j in range of whatever num is. So therefore, whatever's not in the window and the remainder. And this is where they actually begin their sliding of the window. Same concept here. They grab the temporary sum. So they drop the first number and then add the second number to the right of it. Therefore, sliding their window and then using the max to grab the max sum and temp sum, right? Just same concept. Only difference is, as you kind of see the trend here, is the nested for loops, right? The nested for loops really kills you, all right? Especially when working with lists. Depending on how big that list is, it's going to really affect your time complexity. And that's honestly the biggest thing to take away from this is how you write your code. There's more efficient ways of doing stuff than putting it all within a nested for loop. And using these patterns and data algorithms really helps you, gives you that way to avoid these nested for loops, right? The divide and conquer pattern. All right, so this pattern involves dividing a data set into smaller chunks and then repeating a process with a subset of data. Right, this pattern can tremendously decrease time complexity. Several searching algorithms fall within this category, binary search being one of them. The most popular of these will be covered next class. Don't worry too much about that. And I think that pretty much sums up Big O and common problem solving patterns. Before we move on into our next lesson, do I have any questions about anything that was covered? I understand that's probably a lot of information. This is like over 50 slides of information. I don't want to move over to different other algorithms and problem solving patterns before I ensure that you guys are tracking everything that was taught up to this point. Is there anything you guys want to cover or any questions you guys might have? Okay. Yeah, so we're gonna stop here. We're gonna pause for 10 minutes. I realize we haven't taken a break. So take a 10-minute break before we begin the next class. The next class should be searching. It's not here. I'll get it right now. It should be like searching, recursion, different types of algorithms that you're gonna be using. Take a 10-minute break. Time is currently 7:17. Come back at 7:27. All right, let's get back to it. It's gonna be lesson 12, searching, sorting, and recursion. I already updated the slides. You should have access to the slides if you want to open it up on today's lesson and follow through with me. We're gonna get about halfway through of today's lesson. Full disclaimer, we are ahead of our usual schedule. Typically, at this time, we wouldn't be exactly where we're at now. We'd be just starting CSV files, reading and writing. Because for this FoP class, the install phase was taken care of prior to FoP. You've had more time to be able to, essentially get straight into the work. Also, the fact that we've had less days off. So this is going to be a much faster class, which will be nice. The last class was a little bit rushed, so we'll be able to focus a little bit more on some of the classes that were taught. Do some leak code, talk about AI, and actually practice everything we've been learning. So we'll take it a little bit slower than how we usually been doing. We've been going pretty quick. So do not think that we're in a rush. If you guys have any questions, do stop me. Ask the questions. I don't mind if we spend an hour on the same subject if it means that everyone here understands it. So if you guys are struggling, please let me know, and I'll do my best to help you guys out. Well, back to it. Lesson 12: searching, sorting, and recursion. This is getting more into the stuff that you might be able to use the Brocking's algorithm book for. Definitely do check it out if after today's lesson you're very confused. That book will really square you away. The first thing we're going to talk about is searching a list. So a particular item is a very common computational, or searching a list is a particular common computational task. The simplest approach to searching a list for an item is called linear search. An example of that is, when you do a for loop on your list and you iterate through every single item, just searching through it, right? Unless you know the index, then you would have to go through every single item. And that's probably one of the most common ways, but there's ways that we can actually make this faster, and we're going to cover that. So a linear search, as discussed before, is going to be a time complexity of O n. Just to reiterate, what O of n is mainly for people that weren't here yesterday, or it's going to be how we measure how many steps or how fast our code is, right? We use big O notation. O of n is going to be your linear search, where n is going to be the number of iterations your code has to go through to accomplish a certain task. O of n tends to be your second fastest way of doing stuff. O of 1 is your fastest way, being a constant time. It's usually a instant. Stuff like accessing a dictionary via its key is an instant way of doing it. You can another instant would be, a constant time would be accessing the list by its index. You know where it's at. You don't have to look. It takes one iteration, which is why it's O1 being one iteration to do something, right? Second being here what we see now, linear search, O of n, n being worst case scenario, the number of amount of times it has to do something. And lists are horrible for that, because they're notorious for it being the fact that the list of something could be extremely long, right? So n being the number of iterations something has to happen. That's going to be the time complexity. So here we see linear search. A note: the index, opening close parentheses, and the in operator that is used on the list are both linear searches under the hood in Python. So keep that in mind. We did discuss that earlier when we were discussing the frequency pattern of the not so good example and the good example. The not so good use the in method, but it was using it on a list, right? And at first glance, it might look like, we're just checking if it's in there, and now we're not actually doing a for loop. But under the hood, that's what Python is doing, right? So keep that in mind when using some of these methods. And here it's linear search, right? Because we do a for I in the range of the length of a underscore list, right? That could be one item within that list or a million, right? And then inside of it, we do if target, we're comparing, and that's it. But n being the number amount of times we have to run line 3 or 4, right? Best case scenario, we might do it the first time we found what we were looking for. But worst case scenario is we have to get all the way through the end of the list until we get to the last one. Binary search, a more efficient algorithm for searching a list, but only if it's sorted. All right, and you got to keep that in mind. Only if it's sorted. Don't try to attempt it on something that isn't, because it won't really work. Once again, like I have to harp on it. Brocking's algorithm is an amazing way of explaining this. Do check it out after the lesson if you can. Binary search is a part of the divide and conquer pattern we discussed last class. And actually, let's look at that image that they had on the divide and conquer. What did it look like? It started with a list of items or of integers we see here. And here's just a explanation or an example of it. It's looking for something, right? What is actually doing? It breaks the list into two different groups from 9 forward, and then from 3 before it, it breaks it into another two. Now it's in two pairs, and then it goes into fours. And what does it do here? It switches them. It divided the task, and it just. I'm going to go ahead and assume that what it did is it broke it into different parts. It did a compare and contrast between two different items. It checked which one was greater than the other, therefore sorting it. Now 27 is on the left, 38 is on the right. Right, 27 is less than 38. It did the same thing on the next one. 3 and 43. Then 9 and 82, it was the same, so it didn't switch. 10 being on itself because it didn't have anything to compare it to. And then once it gets here, what does it do? It switches these again, right? It switches these to the left, this one to the right, and now it's sorted, so on and so forth, to the opposite side, and then it compares these two to see which is greater than the other. And before you knew it, it sorted the entire list. How? By breaking it in halves, right? And that's kind of how binary search is going to work, right? Binary search is part of the divide and conquer pattern that we discussed last class, which is what we just saw. This type of algorithm focuses on dividing a data set into smaller chunks and then repeating a process with a subset of data, right? And that's what we saw here. It breaks it off into smaller chunks, and it keeps doing the same thing, right? Once it breaks off into chewable pieces, it's doing a comparison and it's sorting it, and you're going to use this method in a little second, right? Moving forward, binary search pseudocode. This function will accept a sorted list and a value. So this is going to be an actual student practice. You'll see on your binary search.py for lesson 12. You're going to create a left pointer at the start of the list and a right pointer at the end of the list, right? So while the left pointer comes before the right pointer, you're going to create a pointer in the middle, right? And then you're going to check both sides, right? You're going to see if the value you're looking for is going to be on the left or in the right. And we can actually draw this out to give you a better explanation instead of just talking through a slide. What's going to happen, and the way binary search is going to work, is that it's going to take a sorted list, right? Let's zoom in a little bit. It's going to take it in a sorted list. And then within this list, we're going to go through it. Let's say just give me 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. What's going to happen is you're going to keep track of 2 or actually 3 different variables. You're going to do the start, which will be at index 0, right? I'm just doing this for, I'm not actually going to code anything. I'm just going to do some more visual representation. The start is going to be the first number in our list. The end is actually going to be our number 10, right? I'm not doing index. I'm not coding. I'm just showing some visual representation here. Which call it, we can actually use this instead. Where we can say start. Jesus Christ, why are you like this? Man, technology, it helps and it sucks. Whatever, you know what this is. You know this is start. It's gonna be our start point. We're gonna want our endpoint within it. And then we're gonna want our middle point, right? We're looking for a number. And what's gonna make it easy for us is going to be checking where it's at, right? So our middle number, we'll start it in the middle of our list. Start will be at 1. And then our end will be at the last item. And as you break stuff up, you're going to, and we're looking, for example, for the number 3, right? We want to look for 3. We don't know where it is, and instead of just searching throughout the entire thing, you assign variables, right? One variable will have the start variable, which is going to be 1. One will have the last variable, right, which is going to be at index -1, right? We can look at the last item in an array by using -1, or we could do the length of the list -1. That'll be an index, and then we can use that as an index to grab the last item. And then you're gonna do you can divide the length of whatever list you're looking for, and that will be your middle. And then because it's sorted, you know that anything after 5 is going to be greater, anything before 5 is going to be less, and you can see, hey, is a number I'm looking for, is 3 greater than 5, or is it less than 5? And you're going to come to find out that, oh, it's going to be less than 5, right? So now what's going to happen is you no longer need anything after 5. You're going to reassign the value of what middle is to, or you're going to actually assign the end first. The end value is going to change from whatever middle was. So 9 is going to equal middle, and then middle will equal the overall length from whatever 1 through 5 is, and that'll be your new middle, right? And then you'll do the same thing again. You'll compare. Is 3 the same as is it greater, less than, or equal to what the middle is? And luckily, because it was a number we were looking for, it is. And we found our number in 2 steps, right? We had to check, we compared 2 items. We compared 5 and 3. It took 2 steps instead of looping through the entire list. What if we were looking for the number 8, or let's say 7? Let's say we're looking for number 7. We start our pointers the same way, the start and the end point. Our middle is our 5. We're going to check, is the number we're looking for less than or greater than our middle point? It's greater. So anything prior to 5, we don't need it, right? We'll change the value of what our start point was to what middle is, and then we'll assign a new middle. It's 7. Let's say it was 6, right? Let's say we're looking for 6 instead. Is it less than or greater than our middle point? Our middle is now 7, but we're looking for 6. It's actually less than 7, so we're going to change anything after 7. We don't need it, so we'll change what end is, get a new middle point. Our start point is 5, our end point is 7, and our middle is going to be 6. Is the number we're looking for equal to what middle is? And yes, it is. That took 3 steps instead of what it would take normally, which would be 6 steps. It just cut everything significantly into smaller groups, which are more digestible. And instead of comparing every single number until we got into it, we only have to compare 3 different numbers. Up to this point, does this make sense, or did I just confuse everybody by all my stuttering? Did it make sense? Right, we're just cutting this bad boy in half, and then if it's not greater than our midpoint, we don't need anything past it, right? If it's less than our midpoint, then we don't need anything before it. And that's what you're going to do throughout the entire thing. You're just going to keep cutting this bad boy into smaller pieces, cut it in half until you find what you're looking for. And this really shines the bigger the list is, right? And you'll see it, right? Because it's hard to explain it. Here it took 3 steps. What if we were looking for the number like 3,000 and within a list of 5,000 elements? You would cut that in half, right? The first step will bring you to 2,500 items. The next step will bring you to whatever half of 2,500. Let's say 12, 2,500, whatever you get. It'll cut it in half. Let's see. Calculator. because I'm pretty dumb, right? So we're looking for our 3,000 within 5,000, right? So we're looking for the number 3,000 within a list of over 5,000 items. We know that the midpoint of 5,000 is going to be 2,500. So it's greater than 2,500. So we divided the bad boy in half. That's the first step. We look for anything past that, from 2,500 to 5,000. Actually, well, let's look for a different number. I feel like I'm confusing you guys. I'm horrible at this, man. Let's look for a number 2,000 within 5,000, right? We divide it by 2, right? We don't need anything past the midpoint because 2,000 less than 2,500. So that was the first step. Now we're looking for whatever is in the middle of this. What's the middle? It's 2,500. It gives us 1,250. Well, 2,000 is actually greater than this. So we'll use the numbers between 1,250 and 2,500, right? And that's it just cut this down significantly. Now we only have 1,250 items to check through, right? And you keep doing that until you reach the number that you're looking for. And instead of looking through over 5,000 different items, you're able to actually get to the number you're looking for within 8 to 10 moves, right? The greater number that we're looking for, or items that we're searching through, the easier and more it's going to shine when it comes to binary search. And it really helps you, especially when looping through a list, right? O of n being the worst case scenario is going to be the max length of that list. Binary search is going to allow you to be able to cut that in half significantly, right? And you'll see that right now. You try out the binary search.py and let me know how that goes. We'll walk through it afterwards. And actually, we'll have a student explain this one. Maybe you guys can explain it better than I did after you try it out. With so coming back, let's look at the binary search problem. Can you guys see my VS Code? Okay, cool. So we have the write function called binary search that accepts a sorted list and a value. It should return the index at which the value exists. Otherwise, return 1. You should use the binary search algorithm. All right, and I'm hoping now that you guys kind of try to use it, you understand it a little bit better, right? So here in the binary search function, we declare 2 variables. One's going to be called left and one's right. We assign one 0, which will be the start of the search point, right? So the left side, and then the right will have whatever the last index is, and that's being gathered here by using the length method on the sorted list and just subtracting that by 1 to compensate for the shifting of indexes. And now we're going to check that while left is less than or equal to what right is, essentially what this is doing is we're always going to be comparing the start and end point to ensure that they will not equal each other. So we know when we actually reach the last couple of numbers, then we're going to do some type of function here. We declare what the midpoint is going to be by adding both the left and the right side and dividing that by 2, giving us the middle index. That's our mid pointer. And then we do if the sorted list, we check if our middle value is equal to the number that we are looking for, then we're going to return that, right? That means we would have found it. And if for whatever reason, the middle value is less than the number we're looking for, then that means it's not on any number before what that midpoint is. So we would add a new left value, which will be the midpoint, right? So if we're looking at this list right here, we're looking for the number 10. The start will be whatever is at 5, and what's at 99 will be the end. And more than likely, our midpoint will probably be somewhere with a 37 or 40. I want to say that the code rounds it up to the next item, or it rounds down. Actually, that's what the double forward slashes does, right? It's a floor method in Python, as we know, so it would run down. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yes, it would round down. It will probably grab whatever is assigned here at 37. And then it would check, hey, is num, which is going to be our value, here 10, is it greater or less than mid? Well, it's going to be less. So anything past 37, we no longer need. So we're going to assign a new endpoint to whatever mid used to be, and then we'll grab a new mid, which it's probably gonna end up being 18 here, or 14. And it's gonna keep doing that as we cut down the list until we find 10. And it's probably gonna take 3 tries here to get up to 10. But instead of looping throughout a list of n number of items, we only took 3 tries, right? Binary search significantly helps us find what we're looking for, and increases the time complexity, right? Did everyone do something very similar to this, or how did it go? Anyone got something different? Okay. Yeah, awesome. So pretty plain simple, very straightforward. We'll move on with the lesson. Where am I at? That was binary search. Here we have an example. They got the first number, which is going to be 0, right? Index 0. Then it grabs the last index. It does the exact same thing. While it's less than or equal to, we're going to do something, right? We're going to go through this list of code between line 5 and 11. They grab a midpoint, and then they check whether it equals to the target we're looking for or not. If so, return it. If it's greater than, then we're going to grab it and everything, what you call it, essentially before the middle, and then so on and so forth. Everything, pretty much what I just did. Pretty simple, very powerful searching method. What's the big O of binary search?
O of
Who
n.
knows? It's gonna be O log of n.
Oh.
I'm pretty sure it's log of n. It's not gonna be O of n. It's going to be what you call it, log of n. Why? Why is that? Who said O of n? Was that Kara?
I did. Is it because it's restricted by the length of the list?
It's not gonna be O of n, right? Because we're not using the entire list, but it's not O of 1 either, right? Remember I told you guys we're gonna be using the log of 2 whenever
Yeah.
this
Yeah, no,
log,
it makes sense.
right? So we're essentially dividing it by 2 the entire time, and cutting it up instead of actually going through the entire n amount of items within that array. It's going to be the log of n because we're grabbing the n amount of items in that list or array and doing it by 2, right? Dividing that bad boy by 2. So it's not exactly O of n. It's going to be O log of n. It's not as fast as O of 1. It's not as slow as O of n, but it's definitely in between both, right? it's going to be significantly faster than O of n. It doesn't have to go through every single item in there. Only about half of half. Let's take a quick break. My dog needs me. It's 8:06. Let's come back at 8. It's 8:07. Let's come back at 8:17, and then we'll finish off the night. Just for the camera. Unfortunately, I didn't get to record prior to getting to it, but we're currently doing bubblesort.py, and we're gonna walk over the code before the end of the night. So the README, we're gonna write a function called bubble sort that's gonna take an unordered list of integers and it sorts them in ascending order using the bubble sort algorithm, right? So first and foremost, we grab the length of whatever the array was or the list to figure out how long it actually is. And that's going to allow us to know what we have to loop through. And it's not the prettiest, like I said earlier, before we got into it, but we did a nested for loop here. We did for I in range of n, and by default, Python starts its range by 0, right? So this is gonna allow us to go from 0 to whatever the length of what our array is, and then we do a nested for loop because we want to check every single item within there against itself. So after we go into for I in range of n, we did for j in range of 0, and here's probably the part you're gonna get confused the most, right? So we want to start an outer loop to get us looping through the overall main array, right? We want to start that loop. Now, once we start the loop, we're grabbing every single item and we want to compare it to everything else. That's why we need this nested for loop in here. But we only want to check so many items. And how do we do that, right? Well, we want to start at the beginning, right? So we do it from range of 0. And then we want to end with only the items that we want to check, right? But as we go, bubble sort, the way it works is that we're putting everything that's already sorted at the far right. So everything that's already been checked and accounted for should be positive, and it should be on the right side. So we don't want to check that item anymore. And how do we do that? Well, by using what currently I is, right? So we start for I in range of n, we start the for loop. This for loop, honestly, is just there for us to keep count of how many times we have to loop through and check everything. Well, it's going to be depending on the amount of how long this array is. And then afterwards, we can start the real code, right? And we'll check for j in range of 0 to n minus I minus 1. And what is this? Well, n is how long the array is. So therefore, this is 1, 2, 3, 4, 5. So n initiates as 5. Well, on the first go around, what is I? Well, I is 0, right? Because there's nothing sorted at the back, so we don't have to really subtract anything yet. So we'll subtract n minus 0 and then minus 1, right? To get the last index, right? Because the length of the list is 5 items long. We want the last index, so we'll do that minus 1 afterwards. And that's going to grab essentially 4. For j in range of 0, 4 is what this will really say. And then we start checking stuff. If the item in index j, which on the first loop round is going to be 0, is greater than j plus 1, which is going to be what's on index 1, then we want to flip them, right? And if it's not greater, then we're not doing anything. So we don't have to add any further functionality. But in this situation, it is going to be bigger, right? So essentially what this becomes is 3, 5, 10, 6, and 1, right? 5 moves over. So that worked, and it goes back up to the for loop here. We're still inside the nested for loop. J now becomes 1. So we check if what's in index 1 is greater than what's in index 1 plus 1, therefore index 2, then we want to flip it. So now this is checking what's here on index 1 and what's here on index 2. 5 is not greater than 10, therefore no logic is done. So it goes into the next item in the for loop. Now J is index 2, right? And it just does that to the very end, right? Once it's completed one iteration through the inner loop, we go back outside to the outer loop. I now increments to 1. We come back into the nested loop. And this is where the n minus I minus 1 really starts making sense. The length of this array is technically 5. We're now on the next loop around, so we don't want to grab the last item because now the last item has actually been sorted, right? We've already checked the entire list. We know that the first item that's greater than everything else should be already there. So now we want to subtract an amount, right, of how many times we've already looped through. Therefore, we subtract I, right? I is pretty much taking count of how many times we've gone through the loop. So n minus I, if this is 5, that becomes 4. Minus 1 becomes 3. So now we're checking what's an index 3, right? So therefore, we're no longer checking what's at the very end. Because 5 was not bigger than 10, 10 was bigger than 6, so they switch. 10 was bigger than 1, so they switch. We didn't want to check 10 anymore because we already know that 10 is the greatest. That's why we did that minus I. And now we're checking with an index 3. And it's going to do that until we get to the very end and everything has been sorted. Does that make sense? Did I lose anybody? Please let me know. Right, I wrote it a little bit to show you guys. This is what really matters, honestly. To begin with, n is going to be the length of what your list is, right? So n is going to be 6. When we first start off the inner loop, I is equal to 0, right? So that the first loop is 6 minus 0 minus 1. They're 5, therefore index 5, and that's where that logic is there. All right. And I think that's going to be enough for today. I feel like it's probably a lot of information. So we'll stop here and call it a night.